Okay, today I want to talk about numerical differentiation. Now, if you want to use the computer to estimate the derivative of a function, the first thing you'd probably think to do is to just go back to the definition of derivative that you learned in Calc 1, right? The derivative is equal to the limit as h goes to 0 of f of a plus h minus f of a divided by h. And you figure, well, if the exact value is reached in the limit, then we ought to be able to get a good approximation by making h small. Okay, that's a reasonable approach. Let's try that. We'll try estimating the derivative by computing this value, f of a plus h minus f of a over h divided by h is, for a small value of h, and I'm going to call this d1a. So d1 is just my notation for the formula we're going to use to estimate the derivative, right? Okay, now we can see how good a job that does by using Taylor series to calculate the exact error term, right? In terms of the, using the mean value theorem with the value of c that we can never be sure of, but nevertheless it'll give us a good idea of what's going on. So recall that the Taylor series says that f of x is equal to, now here what I'm doing is I'm expanding the Taylor series about the point A. So if x is a point nearby to A, then f of x will be equal to f of a plus f prime of a times x minus a, and then plus an error term. So here I'm just doing the first order Taylor series with the second order error term, f double prime of c evaluated at 2. Right, so we don't know what c is, but we know it's somewhere between the center of the expansion A and the point x that we're interested in. Okay, now when we apply it to this formula up here, we're going to be plugging in a plus h, so for x, and therefore x minus a is going to become h. Okay, so rewriting this, we can say that f of a plus h is equal to f of a plus f prime of a times h, and then plus the error term, which is f double prime at c over 2 times h squared. Now, if we plug in this formula for f of a plus h up here and subtract off f of a, then of course this term disappears, right? So then we'll get only these terms remaining. And then when we divide by h, what we'll get left over will be this. So the first term just becomes f prime of a, which is exactly what we want. And the other term is the error term, right? That's the amount by which this expression differs from the value we want. So the error is f double prime of c divided by 2 times h. And again, we don't know what c is, but you can get a good bound on the error this way by considering what the worst case scenario is for c. The most important thing to note here is that this error is proportional to h. So this converges at the same, linearly in h, right? That the size of the error is going to be proportional to h. So that's pretty good. It means that the smaller the h, the more accurate the estimate will be. And that's worked for us so far, right? As long as we can keep reducing h, we can get as accurate a measure of the derivative as we want. Okay, there's one slight problem though. The problem is that we're working on a computer. When h is very small, the difference between f of a plus h and f of a may itself be very small. And in worst case scenario, the difference may be so small it's actually below the machine delta, right? It's too small to even be represented on the computer. If that happens, then our estimate, our formula, is going to give us an estimate that f prime of a is 0. And f prime of a may be nothing remotely close to 0, but that's what we'll get if the difference between f of a plus h minus f of a happens to fall below the machine delta. Okay? Now, even in normal cases, f of a plus h minus f of a is going to suffer from a loss of significance errors, right? Because we're subtracting two terms that are very similar in size, so we're going to lose a lot of significant digits when we do that. So the error could be quite significant, especially in relation to the size of the function, of the true value. So to try to get a grip on this, let's see. I'm going to let epsilon be equal to the actual error in the computer's calculated value of f of a plus h minus f of a. Okay, so that's going to be one source of error in the limits of the computational abilities of the computer. So epsilon is that error. But in addition, of course, we also have the error from the previous page, right? We've got this error, which is just theoretical, right? Even if no matter how small h is, we're still going to have this error. So you combine the two errors together, and you get this expression. We can say that the total error, by using our formula d1 to estimate the first derivative, is going to be epsilon over h plus some constant times h squared. But, that constant is going to be f double prime of c over 2. But the point is, it's some constant times h squared. So here's the problem. We've got one term that is proportional to 1 over h, and we've got another term that's proportional to h squared. One term gets bigger as h gets smaller, and the other term gets smaller as h gets smaller. So the point is, we can't optimize this by just making h small. If we just continue making h small, the first error is going to blow up, right? This error over here is going to blow up. So we're left with a compromise. In order to minimize the error, we have to find some kind of compromise value that's for h that's not too big and not too small. The important moral to take from this is this. Smaller is not necessarily better in this case, right? Making h smaller does not necessarily reduce your error. In fact, beyond a certain point, reducing the size of h actually increases the error. So we cannot simply, get better and better approximations by reducing h. So we have to be very careful about that. That means that it's going to be important for computing derivatives in order to, it's going to be important to get a really optimal formula that we can use to calculate derivatives, right? And we can actually do better than the one we just used, which was kind of a naive formula based on the definition of the derivative. So here's a better formula. I'll call it D2. And what we do is we sample one point on the right of A and another point on the left of A and divide by 2h. Right? So we go h units to the right of A, h units to the left of A, take those two sample points and subtract them and divide by the distance between them, which would be 2h. And you can see intuitively this seems like a better idea because now we're sampling from both sides of the point, right? It does seem like a bit of a mistake in the original, in the formula D1, that we were only sampling from one side of the point, right? That was likely to cause trouble, right, in some sense. So let's do the error analysis again. So this time I'm going to use the Taylor series in order to do the error analysis. This time I'm going to carry out the Taylor series to the second term, and therefore it'll have a second order term, and therefore it'll have a third order error term. So f of a plus f prime of a times h plus f double prime of a over 2 times a squared, and then the error term is the third derivative of f evaluated at c divided by 6, which is 3 factorial times h cubed. Now, if you also plug in f of a minus h, then you just change two of those plus signs to minus signs, right? When the power is odd, then negative h to that power will be negative, right? So just change two of those signs. And now when you subtract these terms, right, if you subtract these two terms, take the first one minus the second one, you get a lot of cancellations. In particular, these two terms cancel, right? Those two terms cancel, and also these two terms cancel. The only thing that's going to be left is the first derivative term, right, the first order term, and also the error terms, which are third order. So when you do that calculation, what you find is that applying D2 gives us this. It's equal to f prime of a plus an error term, which is of second order in h. We lost a power because we divided by 2h, right? We divided by 2h here. So therefore, the h cubed in the error in the Taylor series goes down to h squared. But this is still better than the previous formula we were using, right? This is going to converge like h squared. So this is going to have much more rapid conversions. So this is a much better formula to use, right? And it'll give better results for the derivative. Now, d1, oh yeah, now how would you calculate the second derivative, right? Suppose we want to calculate the second derivative. Well, let me go back to that first naive formula, d1, right? d1 of a, that was f of a plus h minus f of a over h. And we saw that this was not the best estimate for the derivative f prime of a. However, if you think about it, it is a good estimate for the derivative not at a, but at a point right between a and a plus h, right? So if you consider consider the point a plus 2h, suppose we're interested in calculating the derivative at that point, then this point a plus h, it's to the right, and this point a is to the left, so we're sampling on both sides and dividing by the distance between them. So, in other words, instead of thinking of this formula as an estimate for the derivative a, why don't we think of it as an estimate for the derivative at a plus h? And and in that case, it's actually the second formula, the superior formula, right, which converges like h squared. So we can use this formula to get an estimate of the first derivative at a plus h over 2. In a similar way, using the points a and a minus h, we can get a good estimate, basically a d2 estimate, for the derivative at the point a minus h over 2. Okay, so now we've got the derivative at a plus, or an estimate for the derivative at a plus h over 2, and an estimate for the derivative at a minus h over 2. Again, these are points on both sides of a, one on the right and one on the left. So if we combine those and divide by the distance between them, this gives us a good estimate. It should be a second order estimate for the second derivative, right? It's basically d2, our formula d2 applied to the first derivative of f. So this should give us a good estimate for the second derivative of f. Now, if you go back and plug in the formula for d2 in terms of f of a and f of h and f of a minus, f of a plus h and f of a minus h, just plug everything in and simplify it, the formula reduces to this. And so that turns out to be a good formula to use for estimating the second derivative. You take the value of f at a plus h, and also, f at a plus h, also the value of f at a minus h, and you subtract off twice the value of the function at a and divide by h squared. And that gives a good estimate for f double prime. Well, you know, we expect it to be a good estimate. Why don't we do the calculation, find out exactly how good an estimate it's going to be? So let's see. Here, I'm using the Taylor series. Let me try that again. I'm using the Taylor series, but now I'm carrying it out to the third order, right? And we'll have a fourth order error term. So f of a plus h equals f of a plus f prime of a times h times f prime of a over 2 times h squared, f triple prime of a over 6 times h cubed, and f to the fourth, the fourth derivative of f evaluated at some point c between a and x divided by 4 factorial. Did I do 4 factorial divided by 4? Oh, I'm sorry, that should have been 24, shouldn't it? I got to fix that. Okay, I will fix that in the notes, but this should be 24, 4 factorial times h to the fourth. Okay, and then similarly, if you plug in the a minus h into the Taylor series, then again you just change a couple of the terms. You change them from positive to negative. So you change the odd degree terms from positive to negative. And now if you carry out this calculation, you take f of a plus h and you add f of a minus h. So now we're adding these two guys together. When we add f of a plus f of a, we get 2f of a, but then we subtract that off right away. That's part of the formula. We subtract that off. So all the f of a's cancel. The f prime of a times h, that cancels, right? Because there's one in each term there, so those cancel. These do not cancel because they're both identical. When we add them up, we get exactly f double prime of a, and then when we divide by h squared, we get exactly what we want, which is the second derivative of f evaluated at a. Continuing on, when we add up these terms, they cancel. So the third power terms cancel completely, and the only remaining term that's going to be left is the fourth power error terms, right? So when we add these two up, now as I said, it should have been over 24. Over 24. When we add them up, then it becomes over 12, right? When we have two of them, and so that's why the error term looks like this. Right? It should have been the error term is going to be h squared over 12, or actually negative. I should say there's a negative sign there. So the error term is going to be negative h squared over 12 times fourth derivative of f evaluated at this point c, somewhere between a and x. Okay, so that tells us that this formula over here, this formula is a good estimate for the second derivative of f at a, and it converges like h squared, right? So it's just as good as the formula d2 we used to estimate the first derivative, right? It converges just as fast as that one does. It converges like h squared. Okay, I just want to show you one more thing. So we got this right. Second, this formula for the second derivative, kind of intuitively, right? I kind of argued that, look, this should be a good estimate for the first derivative, and then if we take the two estimates for the first derivative, we should be able to combine them to get a good estimate for the second derivative. It was a little bit ad hoc, and mathematicians don't like things to be ad hoc, so let me show you another way that we could have derived that from scratch without making any intuitive arguments. It's called the method of undetermined coefficients. So the way it works is you assume that you're going to get a formula for some quantity you're trying to estimate, and your formula is going to be just going to be a linear combination of some sample values that you're going to take, right? So in this case, we're starting out with the assumption that we should be able to find a good estimate for f double prime at a by somehow combining the values of f at a plus h, at f of a at a, and also at a minus h, right? So if we combine the values of f at those 3 points using some coefficients, right? So we sample f at these 3 points here, and then combine them in a linear way, using some coefficients yet to be determined, then we're hoping that we should be able to get a good approximation for f double prime somehow that way. And the problem is to figure out what a, b, and c are, right? So this is rather similar to the method for finding the values in Gaussian curvature, but this is much simpler. We only have 3 variables, so it's a much simpler problem. So let's check it out. So what we're going to do here is first, I'm going to rewrite the first term as a times, and then I'm going to write out, again, I'm going to use the Taylor series version of f of a plus h. So I'm going to write that out in a Taylor series. Now, b times f of a, well, that's just b times f of a. We don't have to worry too much about that. C times f of a minus h, again, we'll write out that expanding, let me do that again, expanding f of a plus a minus h in a Taylor series, right? So we expand the first and the third terms in Taylor series, and now what happens when we add everything up? Well, it could be quite a mess, but let's try to go about this systematically. We want most of the terms to cancel, right? We want basically we want everything to cancel except the second derivative, right? What we'd like is when we add up these three terms here, we'd like to end up with simply f double prime of a. That would be ideal if we just, and if everything else cancels. Okay, so in particular, we want f of a to cancel. Well, there's three terms here that are going to involve f of a times f of a, b times f of a, and c times f of a. We want those to add up to 0. Therefore, the coefficients of f of a plus b plus c, they must add up to 0. So we get this condition. If we want the f of a term to cancel, then a plus b plus c must be equal to 0. Okay? And then we do a similar thing with the other terms that we want to get rid of. We want to get rid of the f prime of a term, so we want these guys to cancel, right? Now the first one is multiplied by a, and the second one is multiplied by c. So we want a times the first one plus c times the second one to cancel. Well, if you factor out the f prime of a, what's left is a times h minus c times h. So we want those guys to cancel too. In other words, we want ah minus ch to be equal to 0. And then, furthermore, now the one term we don't want to cancel is the f double prime term, because that's what we're trying to estimate, right? So we want to keep that. We would like the f double prime terms to add up to exactly f double prime of a with coefficient 1. So if we add up these two terms, that term is multiplied by a, and this term in the third one is multiplied by c. If we add those up, and again, pull out the f double prime of a, what are the coefficients left? Well, the first one would be a times 1/2 h squared, and this one would be a c times 1/2 h squared. And we want all that to add up to a coefficient of 1, so we get this condition. Let me try that again. We get this condition. Right? We want ah squared over 2 plus ch squared over 2 to be equal to 1. Finally, we would also like, it would be awfully nice, let me try this again. Yeah, it would be awfully nice if these two terms cancel, right? And of course, the first one is multiplied by a, and the second one is multiplied by c. So we want a times this one to cancel with c times this one. This one's negative. That's going to be pretty easy to do. As long as a and c are equal numbers, then these guys will cancel. But to write it out formally, again, pull out the common factor of f triple prime of a, and what's left of the coefficients are going to be a times h cubed over 6 and c times minus h cubed over 6. And we want those to cancel to add up to 0, so that gives us this equation. Okay, now if you look at what we've got a system of 4 equations in 3 variables. It seems overdetermined, like we might not be able to solve it, but in fact the second one here and the fourth one here, they're actually equivalent. They both say that a equals c, basically, right? So from both of those equations you can infer that a must be equal to c exactly. Then once you know that a and c are equal, then you can say from the third equation here that ah squared over c plus ah squared over c, a is equal to c, must be equal to 1, right? So we get this equation. Ah squared must be equal to 1, which means that a must be equal to 1 over h squared. So now we know what a is. That means we also know what c is. And if we plug both those values back into the first equation, we can conclude that b must be 2 over h squared. Putting that all together back here, we get exactly the same formula we had on the previous slide. 1 over h squared times f of a plus h plus 2 over h squared times f of a, I'm sorry, minus, oh right, b has to be negative. Oh, I got to fix that too. I'm sorry. b should be negative 2 over h squared. I will fix that in the slide before I post the PDF file. So minus 2 over h squared times f of a plus 1 over h squared times f of a minus h, and that gives us exactly the same formula we got before. So you can see how you could extend this method to find ways of computing higher derivatives, right? You might want to extend the Taylor series to more terms. You might want to include more sample values, right? If you wanted to find, for example, the third derivative of a function, maybe you'd want to sample it at more places than just these 3 places. But you can use basically the same method to figure out ways to estimate the third derivative, the fourth derivative, or anything. Okay, that's it. And I'll put some homework up, as usual.